Okay, today is September 6th. This is video number 2 for differential equations. Okay, my name is Nicholas Poulter. This problem for this week is a mixing problem. It utilizes aspects that we've learned throughout the past 2 weeks, including initial value and integrating factor. The problem that we were given today involves a man-made lake with 200 gallons total volume at time zero, with 50 pounds of chemical dissolved throughout. The solution of 3 pounds per gallon of a chemical mix flows into the lake at a rate of 4 gallons per minute, and then a mixture, a lake mixture at this point, flows out at 4 gallons a minute. Right off the bat, we can see that the two rates are the same. It allows the volume of the lake to remain the same, which very much simplifies this problem. We are to find the maximum amount of chemical in the lake. To do that, we'll have to utilize steps that we've learned the past 2 weeks with some differentiation. The first major step is going to be to define the formula in which to find the problem. To do that, I find pictures to be very helpful in any aspect of math or any other subject. It allows me to separate variables, distinguish what's important and what's supplementary to the actual variables we're trying to find. I've done that here just to show that, I understand that it's 200 gallons, which is constant. Rate in and rate out are equal to each other, which allows the volume to remain constant. So from there, what we're looking for is Q of T, the amount of salt, sorry, not salt, it's chemical here. Previous problems have made me write salt just out of habit. But I do understand here that it's chemical. The amount of chemical in the water at time T, and not tank, obviously it's lit. So I've defined here based on the formulas given in the notes and the textbook, and also supplemental videos, that rate in times concentration minus the rate out times the concentration. We know 3 of the 4 of these off the bat. Obviously, the rate in and concentration in, and then the rate out. We need the concentration out in order to find the maximum amount of chemicals at any given time t. So that is what we're attempting to solve through our differential integration strategies. So we simplify from this point, 12 minus Q over 50. And this is just for the initial Q, which is 50 pounds, so Q naught is 50, or Q at time 0. I've written it 3 different ways right here. It allows me to better strategize for further problems that I need to use this in, basically use it throughout the remainder of this problem. Just remaining continuous throughout math problems has helped me in the past. I found if I do it, I am much more efficient at solving things and don't have as many errors. So I've outlined that here, but moving forward in the differentiation, we have to utilize integrating factor. That becomes T over 50 from the Q over 50 we have right here. Then differentiating further, we move down and we get QE to the T over 50 equals 600 E to the T over 50 plus C. At this point, we plug in our Q at time 0 is equal to 50. Which will give us our value C, which we plug back in order to further define the actual formula we will need to find the maximum amount of concentration of chemical in the lake. So I've done it here. This completes part B. Part A was the initial setup, which I've shown here. Part B is the actual integration and establishment of the formula. Moving on to part C, which is finding the max amount of chemical in the lake. That was fairly straightforward. As t approaches infinity, as t gets larger and larger, the value in the denominator becomes larger and larger, and takes this value of the second part of the equation to 0. Essentially, when the limit is large, the value is tiny, which leads to the answer of the maximum amount of chemical in the lake is going to be 600 pounds, which makes sense. You have a continuous flow in of saturated water and then a flow out. So at some point, you're going to reach a maximum level of concentration for for the chemical. So I've outlined that here as well.